Welcome to Mathmania Academy. In this video, we are going to discuss the Part B questions of December 2016. Okay, the first question says that which of the following subsets of R4 is the basis of R4? So, if we are given some set and if we have to check that is forming a basis or not, what are the two things that we have to check? The first one is whether the vectors are linearly independent or not. Okay, the second one is the vectors spans the entire space V. These two are the conditions for a set of vectors to form a basis. But when we deal with finite dimensional vector spaces, by knowing that just by looking at it, or by some means if we come to know that it is a finite dimensional vector space, or in particular when we deal Rn over R or Cn over C, that kind of thing, then we have some shortcut ideas that I am telling you. These are some traditional ways which you guys already know. I'll tell you a shortcut thing. That is, if you come to know that this is a finite dimensional thing, it is enough for us to check whether the set of vectors is linearly independent or not. Okay, here we have four set of vectors, right? So first, in order to check the linearly independence, if we will write this alpha j, then the set of vectors equal to 0, then we'll have what? We will have a system of equations with four unknowns. Then we'll have to check that four unknowns, and finally what we end up is that we will have a matrix through which we will solve it, right? So basically I'll start with b2. Okay, as of now I'll take I'll take b3. Okay, let me choose the scalars to be instead of alpha. Okay, let me choose alpha 1 itself. Alpha 1 of 1200 plus alpha 2 of 0011 plus alpha 3 of 2100 plus alpha 4 of -5500, which is equal to 0. Okay, this is nothing but alpha 1 plus 2 alpha 3 minus 5 alpha 4 comma 2 alpha 1 plus alpha 3 plus 5 alpha 4, then alpha 2 comma alpha 2, that is equated to 0. If you put this in a matrix form, what are you going to get? You would get 1 0 2 minus 5 and then what, 2 0 1 5, then 0 1 0 0 0 1 0 0, alpha 1 alpha 2 alpha 3 and alpha 4. This is equated to 0. Okay, you just have to check whether this matrix, determinant of this matrix is not 0. If it is okay, basically this is a system of linear equations, homogeneous system of linear equations. If you treat this matrix as A and this as some x equal to 0, if your determinant of A is non-zero, then trivially x is 0. Okay, now we are checking about the linear independence. Okay, if your determinant is 0, then the vectors are linearly independent. If the determinant is 0, then the vectors are linearly dependent. So this is what we can conclude. So if you just look at the matrix, it is that your first vector is your first column, second vector is your second column, third vector is the third column, fourth vector is the fourth column. Am I right? Okay, what is the determinant of this matrix? In order to find the determinant, you can very well perform row operations. When I perform row operations, here I know that my third and fourth row are same. Hence, rank of A is to the most, at most it is 3. Okay, or okay, let me check. Let me perform the row operations 1 0 2 minus 5. and this would be 0 0, and this would be what, this minus this, so it would be 1 minus 4, so minus 3, 5 minus that thing would give me 15, and I have 0 1 0 0 0 1 0 0, so this is 0 0 0 0. So one operation is this, and when I do the next one, I can very well interchange these things. So 1 0 2 minus 5, 0 1 0 0 0 0 minus 3 15, and the last row is full of 0, which tells me that rank of A is 3 and determinant of A is 0. Therefore this set B3 is linearly dependent one. Okay, this is linearly dependent one. And when I write down the matrix for set B1, this is what I am going to get. So clearly determinant is non-zero, hence it is linearly independent. Likewise you can check B2, that is also linearly independent. So option 1, B1 and B2 are linearly independent, but B3 is not linearly independent, hence it cannot form a basis. Moving to the next question, uh, actually there is a typographical error here. This is Z and this is minus C. Okay, just identify the determinant. D1 is what? A times of YR minus QZ minus B times of XR minus PZ and C times of XQ minus PY. And if you find your D2, it is minus X times of minus BR plus QC and minus A times of YR minus ZQ and minus P times of minus YC plus BZ. So try rearrange the entries. That's it. That is what we are going to do. So minus A YR minus ZQ. We have, let us have it as it is. Then we have B here, minus B here, right? So take minus B outside. From here we have taken minus B outside, so we would have minus XR, and from here we have taken minus B outside, so plus PZ, right? And the rest, from the rest, if you have plus C, then you would have minus XQ from this, and here you would have plus PY. So if you take minus as a common quantity, then what you have? A times of YR minus ZQ. Okay, so minus B times of PZ minus XR. Sorry, I have taken minus outside, right? So XR minus PZ plus C times of PY minus XQ. So if you see, it is minus D1. So option 3 is the right one, right? So in this question, what you have actually do is that calculate these two determinants. That's it. Okay, this is also a determinant one. Just calculate these two determinants and see. The next question is, we have a matrix A and we are asked to find out A power 2015, right? So this is what we'll have to do. Okay, what is A transpose here? So it is again cos theta minus sin theta cos theta. So when you multiply A with A transpose, what you are going to get is that 1001. That you can very well check. Why am I saying this? Because whenever we study about orthogonal matrices, this is the one example that is there in every book. Okay, so basically what we have is an orthogonal matrix. So you can easily find out what is A power n. This is going to be cosine n theta, sin n theta, minus sin n theta, and what? Cosine n theta. Or if you can very well perform a square just by multiply a and a, then a cube, a square and a, then use induction hypothesis to arrive at this stage. Okay, so a power 2015, this is what we need. Okay, this is cosine 2015 and theta is given to be 2 pi upon 31. Okay, so this is what we need. So basically we shall calculate these things separately. Cos 2015 into 2 pi upon 31. So if you see 31 into, if you multiply it for some many times, like, okay, try to divide this 2015 by 31. So 31 means if you do it for 6 times you would get 186. This is 5 5 155, like, yeah, this is what we are getting. So 5 155, yeah, this is nothing but cos 65 times of 2 pi, which is cosine 135. Since it is an even one, we will get 1. Am I right? So what is sine 2015 into 2 pi upon 31? So it is sine 130 pi. So sine n pi is 0. So basically what we are going to get is 1001, which is nothing but the identity matrix. That's it. Okay. Next question is, J is given to be a matrix of order n by n with all entries 1. So basically this J is a matrix 1 1 1 1 1 1 1 1 1 1 1 1 1 1. This is okay. What is the rank of J? It is 1, because it has only one linearly independent row or a column. The remaining are the same. So rank of J is 1. Okay. And actually in this problem we are asked to find out the rank of B. Okay, rank of B, and B is defined in this fashion. So this, the first this 0 0 J, this has rank 1. Okay, this 0 J0 has rank 1. This J00 has rank 1. Okay, so from this we get only one linearly independent row. Let us have it as a row. Okay, from this we get only one independent row. So from this we get another one independent row. From here we get another one independent row. And when we check these three rows, they are independent. So rank of B is 3. No matter what your n is, rank of B is 3. Okay, moving to the next question. Here I think here also we have some typographical thing. It is S2 and this is S3 and this is 1. Okay, which of the following sets of functions is a vector space over R? So this is what we will have to check. So first let me do the one like, let me choose two functions from S1. Okay, then let me form a linear combination with this thing. If I choose these things from F1, what happens? Limit x approaches 3, f of x is 0, f1 of x is 0, and limit x approaches 3, f2 of x is also 0. So in order to justify that this is present in S1, I'll have to check limit x approaches 3, this thing is 0. So this is nothing but alpha times of limit x approaches 3 f1 of x plus beta times of limit x approaches 3 f2 of x. This one I am able to do by knowing the properties of a limit. Okay, so this is nothing but what, alpha times of 0 plus beta times of 0, which is 0. Okay, when I do this for the function g, that is the set when I take from this thing, limit x approaches 1, g1 of x is 1, and limit x approaches 1, g2 of x is 1. So when I perform these things, limit x approaches 1, alpha g1 plus beta g2, I would end up with alpha times of 1 plus beta times of 1, which need not be equal to 0 always. This is one way of justifying that this S2 cannot be a vector space. Okay, and actually as of now I am checking the subspace condition, and it is asked to verify it is a vector space or not. There is a connection between these two things. As of now, let us check whether it is a subspace or not. We are checking only the subspace condition, right? And if you go for the third one, if you choose h1 and h2 in s2 s3 sorry, then limit x approaches 3 h1 of x, this one exists. Similarly, x approaches 3 h2 of x exists. So if exist means what? This is equal to some L1 which is a member of R. This is equal to some L2 which is again a member of R. This L1 and L2 does not have any relationship between them. Okay. When you perform these things to this one, like when you take limit x approaches 3 to this one, what you will get is, so this is what you will get. Okay, alpha L1 plus beta L2. Your alpha, beta, L1, L2 are real numbers, so hence this is also a real number. So this is also a subspace. Okay, as of now I am talking about subspace. These are subspace of what? Set of all functions, no matter whether they are differentiable, whether the limits for such functions exist at all the points, no matter what, set of all functions from R to R is a vector space over R. This is one of the classical example that we study when we study about vector spaces. Okay, here this S1, if I consider this set to be my S, then my S1 is a subset of S and S2 is a subset of S, and this S3 is also a subset of S, because they are collecting functions from R to R which satisfy certain property. But in S I do not impose any property. Okay, all these are subsets of S. Okay, whenever we say a subspace, that itself forms a vector space. That is what the definition tells us. But in order to verify it is a subspace, it is sufficient to check this condition. That is what I have done. Okay, I am considering set of all functions from R to R as a vector space over R, and I am treating these three functions as a subsets of that space, and I am checking the subspace condition. This is one way. Or if you have to verify the other way, yes, you are free to do it. That is verifying the vector space conditions. Abelian group under addition, the scalar multiplication is well defined, and the conditions that connects the scalar multiplication and the vector addition. And while checking the second option, I was telling about one more thing. We can very well check whether 0 is in S2 or not. Okay, if 0, like suppose 0 in S2, suppose 0 is in S2, then what? Limit x approaches 1, 0 is not equal to 1. Therefore 0 cannot be in S2. If 0 is not a member of some subset, that cannot form a subspace. Okay, through that idea also we can justify that S2 is not a subspace. So S1 and S3 are vector spaces, not S2. Moving to the next question, here we have a matrix which is defined from, okay, actually it is a matrix of order n by m. Therefore this can be treated as a mapping from Rm to Rn. Okay, with each entry equal to 1 minus 1 or 0, such that every column has exactly one and only one entry. Okay, this is what they are saying. Then what can we conclude? This is what the question is. Okay, the rank is n minus 1, rank is m, and some relation between n and m that is given. Okay, Here and all they are saying n has to be smaller than or equals n, which means row has to be smaller or row and column can be equal. Okay, suppose let me try to construct something different. In third and fourth options they are saying that n has to be smaller than or equals m and n minus 1 has to be smaller than or equals 1. So let me choose two columns and four rows and I'm checking whether it is satisfying the hypothesis of the theorem or not, but because my intuitiveness says those two cannot be true. Okay, and each n like in each column we must have only one and one minus one, the rest has to be 0. So let me choose this matrix. Then what happens? What is the rank of this matrix? Rank of this matrix is 1. Okay, and here n is 4, m is 2. So it is clear that n is not smaller than or equals m, as well as n minus 1 is not smaller than or equals m. Out. So rank of A is m, which means 2, but I am getting 1. So this option is also out. Since this is a part B question, this has to be true. So by discarding the options, I have proved option 1 is true. Or if we have to prove it theoretically, that also I can do it for you guys. Okay, since A is defined from Rm to Rn, A transpose is defined from Rn to Rm. Okay, in A transpose, what is happening? In each column there can be only 1 plus 1 and 1 minus 1 and the rest entries are 0. Therefore, each row sum in A transpose is 0. Okay, so we have some ideologies from linear algebra that we know if each row sum is alpha, then this alpha is an eigenvalue, and for which this 1 1 1 1 1 1 n times this transpose is an eigenvector. Okay, so using this ideology, 0 is an eigenvalue of A transpose. Okay, so it is not here we are not talking about a particular row, we are talking about all the rows. Okay, if in all the rows the sum is same, then these things are true. So here what happens? A transpose product with 1 1 1 1, this ones is 0. 0 into the same thing we are going to get 0. Okay, so therefore this means what? This 1 1 1 1 1 transpose, this row vector is a member of nullity of is a member of null space of A transpose. If it is a member of null space of A transpose, then the nullity of A transpose is greater than or equals 1. No matter how many elements are present in it, I am able to visualize one non-zero element in the null space, hence the nullity is bigger than or equals 1. Now apply rank nullity theorem to this A transpose. So rank of A transpose plus nullity of A transpose is equal to n. Okay, I am getting this nullity of A transpose is greater than 1. So what will be my rank of A transpose? This will be equal to n minus nullity of A transpose. Since this is greater than or equals 1, this is less than or equals n minus 1. So rank of A transpose. Okay, we know that rank of A transpose is same as that of rank of A for any matrix A. This is smaller than or equals n minus 1, and that is the first option. Okay, this is the theoretical way of justifying rank of A is smaller than or equals n minus 1. Moving to the last question of this video, here we have a matrix and we'll have to check whether this is a positive definite or not. Okay, positive definite or negative definite. The definiteness we'll have to check. Observe given matrix is real symmetric one. Okay, so if it is a real symmetric one, what are the ways? You can check the principle, like what is 1 by 1. So 1 by 1 is this one, then 3 minus 1 minus 1 2, this is 6 minus 1, that is 5, and determinant of the entire thing, it is 3 times of 6 minus 1 and plus 1 times of 1, so it is 15 plus 1, which is 16. So all these are positive. We can conclude this given matrix is positive definite. Okay, we have identified this is positive definite. This is one way of justifying it. The other way is to find the eigenvalues and check all the eigenvalues are positive or not. That you can do. Now let if I choose this matrix as A, let me define the corresponding quadratic form of this A. Okay, this is x transpose AX. So if I find what it is, and here this x is nothing but x1, x2 and x3. So if I see, I would get 3x1 square plus 2x2 square plus 3x3 square minus 2x1 x2 minus 2x2 x3. So I have x1 and x2. So x1 square plus x2 square minus 2x1 x2 I have. Okay, then I have 2x1 square extra, let that be. Then x2 square plus x3 square minus 2x2 x3, and I have 2x3 square extra. So this is x1 minus x2 whole square plus x2 minus x3 whole square plus 2x1 square plus 2x3 square. Okay, all these quantities are squares. So this is greater than or equal to 0 for all x in R3 and strictly greater than 0 for all non-negative 0 in non-zero x in R3. By definition also we are able to prove that this is a positive definite matrix. So that's it in this video. Thank you.